Hello, everyone. Thank you for coming. We're happy to have Shafer Smith with us today. Shafer is at the Center for Atmosphere Ocean Science at New York University within the Courant Institute of Mathematical Sciences. Shafer got his PhD in physics back in 1999 from University of California, Santa Cruz. After that, he spent 3 years at GFDL, the Geophysical Fluid Dynamics Lab at Princeton. And after that, he moved on to New York University, where he has been ever since. And go ahead and take it away, Shafer.
And where Sam graduated from our program. He was, no, I graduated from the math program, but yes.
Yeah.
He was a former student amongst us. Yeah. So. Thank you, Sam. Yeah, so I'm Shafer. I'll share my screen now and, oops, wait a second. Okay, there's my first slide. Hopefully everybody can see it. I think Sam is going to pipe up and let me know if somebody's put in a chat message, because I can't see anything. I can't see you or myself or chat messages. We tested, so rely on voice or Sam. So, and I have to say from the beginning that I don't know very well the spectrum of the audience background. I'm assuming everybody's got basic GFD. I know there's not a lot of oceanographic types right now in the department, but hopefully this will be interesting nonetheless. So I'll get started. So I'm going to talk about things related to the parameterization of mesoscale eddies in the ocean, and why they're parameterized, and a focus on one particular problem, which is what kind of led me into working on this in a roundabout way, which has to do with work I'm involved with at New York University, Abu Dhabi, that has to do with modeling distributions of oxygen in the Indian Ocean. And I'll mention a kind of motivating problem from CMIP models about trying to get oxygen right in global models briefly. And so the main thing is that the parameterization, and the issues of parameterization and why we need to do it, and then there's the issue of how do you improve and understand these parameterizations, which relies on our ability to measure eddy fluxes in truth simulations with sufficient resolution to resolve the mesoscale field. And it turns out that even in a high resolution model with plenty of space to store all the output, it is still challenging to extract what the fluxes are. And I'll get into that, try to explain why it's challenging, and show a method that works pretty well, try to convince you that it works well, and then try to look a little bit at what this says about the underlying theory for parameterization, particularly the Gent-McWilliams and Redi parts, which I'll explain to you if you don't already know. So a really fuzzy large-scale view on the left is a VISO sea surface height anomaly from many years of satellite altimetry, measuring the sea surface height, regridding it, taking a time average, and then subtracting off the time average to see the deviation. And because the effective resolution of the satellite altimetric measurements when regridded have an effective resolution of about 100 kilometers at those scales in the ocean, the flow is pretty reliably geostrophic. So the sea surface height, it tells us about the upper ocean velocities, the sort of velocities in the thermocline and above. So you can think of it as, you can think of what you're looking at there as something like a stream function for the eddy velocity field in the ocean. It's the eddy part because the time average has been subtracted off first. Okay, that gets into how do you define an eddy, and this is the eddy is defined relative to a time average, and there's a whole story there which I'll avoid. But so the main feature in a fuzzy sense is that what's the kind of typical scale. I just realized, so using my mouse, I think it's a little problematic.
Good point.
Yeah. Was there?
I think in the past, if you share your whole screen and do the slideshow, then you see the mouse.
Yeah, let me try that. I'll stop that share, and I'm gonna.
Sometimes if you share an application, it comes through, but I guess apparently not this time.
Okay, so now I think we see the infinity, and then I'll put this on top. I think that if I put it, I'm afraid that if I put it in play mode, yeah, I still don't see the mouse. So
I see it. I can see it.
Oh yeah, but I can't. So I don't know where I'm pointing.
Oh no.
Let me try that again. Double check. You see my mouse, huh?
Yeah.
Wow, that's so. Yeah, I cannot see it, so that's kind of pointless. All right, let's see. If I just do it, I could. I don't have any fancy movies, and I think this is pretty big, right?
Yeah.
On the screen. So maybe I'll just leave it like this because this way I can see my mouse and you can see it too, right?
That works.
Okay. If you look at sort of a typical scale, right, a typical divot in this so-called supposed stream function field, what's the typical scale? Oh, you also see my notifications up there. Maybe I should end that. Hopefully not too many come in. The typical scale of a little circular-ish feature in this stream function tells you something like roughly the scale of an eddy. And of course, those features are roughly on around 100 kilometers across. They are larger near the equator, where the deformation scale is large, and smaller as you go towards high latitudes. So they range really from maybe a few hundred kilometers down to tens of kilometers in the Antarctic circumpolar current. So typical climate resolutions are, climate model resolutions are, of course, right about at that scale. If you want to run a fully coupled climate model, global climate model for many years and do sensitivity tests and ensemble averages, of course, you can't afford to have an ocean model that's more than maybe the best would be a degree, more likely a couple degrees or a few hundred kilometers across in resolution, which means that you are cutting off, your resolution lies right in the middle of the peak of the kinetic energy in the ocean. And most of the kinetic energy in the ocean is in fact in the Eddy field. And what's generating those eddies is, of course, baroclinic instability, which has a peak growth rate around that same scale, around the deformation scale. The eddies tend to be a bit larger because there's an inverse cascade. But overall, when in a climate model resolution, if you do nothing else, you've basically removed most of the source of baroclinic instability and thereby have a hugely suppressed eddy field in the model. And so the first question you might ask is, well, so what? What do they do? What's important about that? See this way. So here's my extremely broad, almost glib overview of all of eddy parameterization history. And there were two major problems in early models of the ocean in the 70s that showed up. One is that if this is from an idealized model that consists of a channel and a kind of closed basin above it. So think of it roughly as mimicking something like the Atlantic and the circumpolar current in the Southern Ocean. And it's wind and buoyancy force, a paper by Henning and Vallis, 2005. And they ran cases with and without eddies, so low resolution and high resolution. And it just gives a kind of nice, there are many papers you can see this, but this gives a kind of very nice, almost cartoonish view of the difference between the two. In this it makes sense to start by looking at the eddy permitting case, where the Southern Ocean, this idealized Southern Ocean, looks something like the real Southern Ocean, in that we have, for the ocean, relatively steeply tilting isopycnals. So that actual slope, of course, this is hugely contorted. These axes are, going from 50 south to that should say north over there. That's a funny typo. That's from the paper. So from 50 south to 50 north. I guess this is up to the equator. It's 50 south up to maybe 10 degrees south, it looks like. And of course, that's the equator. You can see the Ekman pumping of the subtropical gyre there. those typical slopes are actually about 1 in 1,000, but they are steep enough to contain a lot of available potential energy. And what sets those slopes is a combination between the Ekman flows, so there's a wind coming out of the page in the Southern Ocean, and in the Southern Ocean, the Ekman flow in the upper ocean is to the left of the winds. So the wind coming out of the page gives me a flow to the right. So the Ekman flow is trying to push all the isopycnals vertical, creating more and more potential energy. What the eddies then react to that, all that available potential energy, generates baroclinic instability and a rich eddy field that basically it generates an eddy-driven overturning circulation that counteracts the Ekman transport, and you get some mean state, mean stratification that is a balance between those two, and where there's a reasonable eddy field and reasonable transports, etc. When I don't have any eddies, what happens is you only have the Ekman pumping, and there's insufficient eddy generation to relax the isopycnals at all. And what happened, so this is an idealized model from not that long ago, what happened in early models run without eddies and without an eddy parameterization is that then sets off the model's convection scheme, and you end up producing deep convection all over the Southern Ocean, which is not what happens. So you end up with, from a purely adiabatic effect, by the way, right? This whole process of eddies relaxing the isopycnals towards some intermediate neutral slope is an adiabatic process. If that adiabatic process, when it's not there, sends the model into an entirely different configuration and changes all the interior water masses to produce this deep convection. Okay. On the other hand, another problem was the fact that so the ocean, to a very large degree, mixing is primarily along isopycnal surfaces, along surfaces of constant density. So since it's largely atmospheric dynamics crowd here, I'd say that one way to think about the fundamental difference to me between the atmosphere and ocean is that in the atmosphere we think of it, you start by thinking of radiative convective balance. So some mix of radiation and convection sets your stratification, and then the stratification surfaces give you a thermal wind balanced wind, and then you get eddies and some complete mean state. The ocean, I think it's a little bit different in that at the 0th order, there's almost no radiation in the interior. The winds and buoyancy surface forcing occur almost entirely at the surface of the ocean. So it's those two forces which are acting to set up a mean current field in the ocean. The density surfaces adjust to be in thermal wind balance with that imposed velocity field. And because there's no radiation, there's, to a really good approximation, nothing to change the kind of integrated density between two density layers, say here, unless they're outcropping at the surface of the ocean. Okay, so, and of course, even from here, you can see that in many places, those isopycnals tilt a lot. The early ocean models, of course, knew that there's much larger, modelers knew that there's much larger diffusion in the horizontal direction and in the vertical direction. But they, it was first coded up as having a different a horizontal diffusivity and a vertical diffusivity, which were very different. But because, if you have a large horizontal diffusivity, a region where the isopycnals are a little tilted, then the effect is to do a lot of mixing across the isopycnal surfaces. In other words, diabatic mixing, not adiabatic, which changes the water masses. So this was called the Veronis effect from a paper by George Veronis in 1975. And so those are two big problems. This is not the solution yet, but this is what two huge problems you have if you don't do anything to parameterize eddies. So here's some of the solutions. So there's the Veronis paper. first part for the Voronezh effect was a paper by Martha Redi in 1982, who wrote only one paper in oceanography, and it's a hugely cited paper, and then went on to have a career in MHD. Anyway, she had a short, nice paper said simply, you know, if you start with, don't think about just horizontal and vertical mixing, and I'll show this more exactly later mathematically, but if instead we rotate the mixing and write it as a tensor and rotate it locally to a coordinate system that is aligned with the isopycnals, so that what we called horizontal is now isopycnal and what we called vertical is now diapycnal, then you can ensure that what you intend to be a long isopycnal mixing, much larger, is really a long isopycnal and it does not cause spurious mixing of water masses across density surfaces. The other big advance was Gent-McWilliams, 1990, who proposed a way to impose an adiabatic thickness diffusion, which basically acts in a very rough sense the way baroclinic instability happens. Baroclinic instability, I don't know if people can see my hand gestures. I'm probably a little postage stamp on your, but you know, I'm lifting my arm kind of in a slope. When I have a slope and an isopycnal potential energy, and I generate eddies, and the effect of the eddies is to try to relax the isopycnal. So if you think about the thickness between two isopycnal surfaces, and if I think about writing, say, the model as a stack of shallow water models, if I have a diffusion on thickness so that I spread thickness out, it's going to tend to do the same thing. It's going to tend to flatten isopycnal surfaces. But using only thickness, I don't change the net mass between two isopycnal surfaces. So it's effectively adiabatic. So Redi solves the Voronezh effect, and the Gent-McWilliams solves the problem of having two steep isopycnals and setting off convective parameterizations. Since then, of course, there are many other papers that have greatly advanced this and tried to understand how to set the GM coefficient appropriately. There's been a lot of work on that. And by the way, there's a missing thing. There's been very little work on understanding how to the Redi coefficient. And in fact, one of the reasons is from this beautiful paper by Steve Griffiths in 1998, where he showed that you could represent these two parts, the Redi and GM parts, in one mixing tensor formulation, where the Redi stuff is all done by the symmetric part, and the GM is done by the antisymmetric part, and then that whole structure collapses and becomes very beautiful and easy and efficient to code if you set those two coefficients equal. And I'll show you explicitly what these are. But hold that in mind, because a kind of major claim at the end is that's been known for other reasons anyways, that these two in fact are very different, and I'll try to demonstrate that they're different in this very controlled situation I'll get into. Okay, so that's the history, and now I'm going to cut into a bit of the math of the parameterization. So over here is a little schematic of, imagine these are isopycnal surfaces, those black lines, and then just cut them off arbitrarily. And so there's isopycnal between two. And what's going on in here, there's sort of three things that we're trying to parameterize in the model. One is the diabatic diffusivity. So before, and I mentioned the Voronezh effect, I'm sort of ignoring that entirely, but this is what the Redi part would be, the vertical diffusivity. So this is the thing that in the ocean and measurements from Ledwell et al. In the 90s releasing tracers is found to be on order 10 to the minus 5 meters squared per second. Some places up to 10 to the minus 4 squared per second. That value is mostly from breaking internal waves at interfaces, and those breaking internal waves are happening on kind of vertical scales of meters and horizontal scales of maybe tens to maybe 100 meters largest. And it averaged out, it gives you an effective diffusivity of about 10 to the minus 4, 10 to the minus 5. By contrast, if you measure how things spread in the ocean along isopycnals over scales comparable to the scale, and then you try to back out a diffusivity. The typical value for that along isopycnal diffusivity, which here I've called kappa y, is about 1,000 meters squared per second. So there's literally a 7 to 8 order of magnitude difference between the size of those two diffusivities. And of course, whenever you're trying to do something where you have a huge number, a tiny number, and getting the tiny number right and not having any of this affect that, that's always a difficult problem. The third part is the more complicated part in a way. This is the adiabatic part. And you can think about it as a sort of out-of-plane stream function that is acting to try to torque that surface back down. The steeper it gets, it reacts and wants to push it back down. That would be the GM part. Okay, so that's the that's the picture. And I also drew in here, right? Why do you care about? So the GM part is acting on the isopycnals themselves. KY and D, kappa Y, kappa D, are acting on a tracer. So it's very important also to remember that one of the most, arguably the most important role of an ocean model in a climate model is its effect on transport of tracers like heat, oxygen, anthropogenic carbon. So I've made a little shading in this picture of light to more blue, indicating a kind of a long isopycnal gradient of a tracer. So, well, let's just imagine the lighter part is the higher value, otherwise that arrow would be backwards. So that diffusivity that you impose in your parameterization is trying to mix tracers along an isopycnal. And this is the part that the Redi part corrects. Okay, so on the right here, you can start by just thinking about the advection diffusion equation for a tracer. 3-dimensional velocity field, 3-dimensional tracer concentration field. And I'm going to assume that the velocity field is incompressible, which is reasonable in the ocean. If I've already done some kind of, it's a little bit sloppy, I should have some bars over there too. Imagine you've done a Reynolds decomposition. You're going to have one term left over, which is the divergence of the Eddy flux, prime C prime, which I've written on the right-hand side. So the way to represent that mixing of the tracer, and by the way, so B, the buoyancy, C could be B. B, the buoyancy in oceanography, we mean is just a nice way to write the density. So think of B as just the densities. Constant surfaces of B are these constant isopycnals, the black lines. So when it's B, of course, changing B changes the dynamics. It's not a passive scalar, it's an active scalar. C is passive. But the structure of that equation is the same, and the way we parameterize those things is the same. So if the first step is to simply assume that that flux can be written as a diffusivity tensor times the gradient. Imagine there's a C bar there, the gradient of the mean tracer field. What that mean is and what the eddy is an issue, which I'll come back to. But right now, just think of it as a pure Reynolds average that maybe is something like a scale separation average. Small scale is the primes, and large, the bars are the resolved large scales. You can also think of this here, I put defined as, you might also think about this as, say, the first term in a Taylor expansion of this eddy flux about the mean gradients. And if I kept all the higher derivatives of the mean gradients, I would get a larger and larger structure, and eventually I might be able to fit all the fluxes to all the tracer gradients in the model. At that point, it's sort of in the same way, if you overfit a curve, you learn nothing. You don't necessarily want to do that, but I just want to point that out. But here, let's just assume that this is an exact representation of that eddy flux as a tensor times the mean gradient of the tracer. Okay, so now this is the C is this is in 3-dimensional space. V has 3 components, X, Y, Z. So there's 3 flux components: a component in the X direction, the Y direction, and the Z direction. And the gradient has 3 components. So this K is a 3x3 tensor. And I can always take any tensor, and I didn't write this part, and break it up into a symmetric and an anti-symmetric part by simply adding it to its transpose and dividing by 2, or subtracting it from its transpose and dividing by 2. So that's how I can always write any matrix that way as an antisymmetric part plus a symmetric part. Why does that matter? Well, first of all, so the Griffey's 1998 paper essentially showed that I can represent the Redi part and the GM part by putting the GM part into the antisymmetric part of this mixing tensor and the Redi part into the symmetric part of the tensor. And Sx and Sy are the components of the mean buoyancy slope. So the horizontal gradient h of B divided by the vertical gradient of B with a minus sign is the slope of that surface. So basically, you can think about each of these components, why they're arranged like that, I'll come back to in a second. Each of these components is sort of, when there's a slope in the x direction, this thing is going to have a non-zero value, and it's going to diffuse at some rate set by the value of this coefficient times that slope. And once that goes to 0, there's no diffusivity. And let me mention this, skip over to here first before going to the bottom part. So it looks unfamiliar and strange if you don't already know this stuff to write it as an antisymmetric tensor. The trick is to realize that if I stick those guys up into here, the divergence of A times grad C, which is here, I can always rewrite the divergence of an antisymmetric tensor times its gradient as a non-divergent velocity dotted into the gradient of C. And that non-divergent velocity can be written in terms of a curl of a stream function. And that stream function has two components, and they are these two values. There's basically kgmsx and kgmsy. One of them is one component of psi, the other is the other component of psi. So this is something you can work out a little bit, or you can trust me for the moment. The main thing about the antisymmetric part is that it can be rewritten as a non-divergent velocity times grad C. So now you imagine you take that part, you've separated it out, and you can put it back over on the left-hand side of the equation, and it looks now like V has just been modified to V plus V star dot grad C. And that V star is what's often called the bolus velocity. Okay. The other part, the symmetric part, so this is, I've written this in a funny way that I'll come back to. This is all, imagine this is all in the geodesic coordinates, the XY coordinates of the model. So instead of just writing, and so if I took the symmetric part and I just put, say, kappa H, kappa Z there without this stuff, that would be like having two equal horizontal diffusivities and one different vertical diffusivity. Instead, write it this way. This was what Redi suggested to do, is to write it in diagonal form this way, but then, and so this is as if you're in the frame that's oriented with the isopycnal. So those 2K Redi components would be acting along and out of the page, into and out of the page and along this isopycnal surface, and kappa D would be the part going across. But then rotating it, using two rotation tensors to rotate this thing, which was written in isopycnal form, back into the lab frame, into the geodesic frame. So then you get all these off-diagonal terms, which I'm not writing down. I'm just kind of writing it in this compact form. But that's the idea. You now take this symmetric part, write it diagonally in isopycnal, and then rotate it back to the XYZ form. I hope that if anybody has a question, you'll stop me or speak up or ask Sam to bug me. Another way to think about the GM part that might be more familiar if you know a little bit about this but haven't seen it written that way is, you know that the GM stirring is like one way to think of it is that it's a lateral down gradient buoyancy flux. So meaning if I just think in horizontal plane x, y, and I see more buoyancy over here and less buoyancy over here, the GM is, you can also think of it as just diffusing density, but it does so in an adiabatic way in the following way. What does it mean to be adiabatic? Here's now my three-dimensional eddy flux buoyancy. So this is a vector in 3D space. If it's adiabatic, then that flux of buoyancy routed into the gradient of buoyancy should be 0. Right? That's what it means to be adiabatic. So, but now I write this as a horizontal part and a vertical part. And I say, okay, what did I say before? Lateral down gradient buoyancy flux. So I take that horizontal part, I write it as a down gradient diffusion of buoyancy with the GM coefficient. Stick that into there, solve for W prime B prime, and I now get an expression for what the vertical buoyancy flux must be in order to end that the overall parameterized buoyancy flux is adiabatic. If I use that for this there, and I use this expression for the vertical buoyancy flux there, I'll get 0. And you can make a few more steps to actually write this as to write the GM bolus velocity in terms of kappa GM and that isopycnal slope. That's not so important. Okay, so that's sort of an outline now of the history and kind of the way that most models actually parameterize and include these effects and try to, so they give you the stronger along-isopycnal diffusivity, smaller diabatic diffusivity, and they have an adiabatic restoring of density surfaces, flattening of density surfaces intended to mimic the missing baroclinic instability in a climate resolution ocean model. So now the problem is these. So if we want to figure out, the trick is what are that kappa Redi and the kappa GM? How could we? You can just go straight to your theory tool bag and try to guess what they should be. But in the end, of course, you'd like to check your theory for those things against a measurement of those two coefficients. How can I measure those coefficients which we know to be flow dependent? I know if there's a region, for example, where there is more eddy activity, in the parameterized run, I probably want a larger GM in that region. And how do you figure that out? So this slide is about the kind of, well, the basic difficulty. It's not complete. Let me try to explain what's here. This is about the problem of measuring eddy fluxes. So think again about a tracer in 3D and function of time that's affected by some non-divergent flow. Same equation there. And now I've just added the bars. I've Reynolds averaged that. This is exactly the same equation I'd written before, but I've now defined that eddy flux of tracer as F super C. So the mean fields are resolved fields. The resolved fields here are affected only by the divergence of this eddy flux. So if I want to think of, and I'll cut forward here, if I want to, most parameterizations tend to think of that flux divergence. If you assume that this flux is primarily down gradient, and then take its divergence, okay, it work for this part. But if I also try to understand the variance of the tracer, I can write down, after a little bit of work, the expression for the averaged variance of the tracer. And on the right, you'll see a grad C bar dot into this eddy flux, whereas here it's the divergence of the eddy flux. This part now, if the actual flux has both a gradient part and a rotational part, that rotational part will go away here. It will not go away here. And this is both potentially a problem for trying to represent fluxes in terms of a pure down gradient diffusion, and it's also a measurement problem because it's extremely difficult to separate out these two parts if I measure the flux. So what am I to say here? Imagine I want to take a high resolution model and I say, okay, well, I can just measure this flux. I put in a tracer, I can save as many snapshots as I want of the tracer and the velocity field. I can define my average and hence define the eddy parts and compute these eddy fluxes at unlimited spatial and temporal resolution if I've got a big enough computer and enough time. And then what? So the problem is if I want to extract and think about how do I parameterize that, well, most of our thinking is based along the ideas of assuming some kind of down gradient diffusion. But in fact, what you find when you measure that in any model is that there's actually a very big rotational part that is considered, while in the real flow it would affect the variance, we don't want to represent it in the flux. In fact, if you just assume that that whole flux is the divergent part and include that rotational part, you'll get a very wrong estimate of what the actual eddy flux is, and hence get the wrong estimate for the GM coefficient. So there's many, many papers that get into the game of trying to find an optimal way to separate the divergent part from the rotational part of a measured flux. The problem is that's an ill-posed problem. Without adding unphysical extra boundary conditions, there is no single unique way to separate those two flows. So it's a bit of a trap. So I'm going to throw that out, and okay, I guess what am I doing here? I'm going to come back to in 1 second to another way to do that. So I'm going back to the same slide. It looks the same. I've changed just a little bit here. You'll see in a second. I'll flip back to the other slide. So suppose we could directly measure this K. So not the flux, but the 9 components of the diffusivity tensor. Then what? Well, if we can measure those parts, then we've effectively separately measured the antisymmetric part and the symmetric part. I'll come back to what I mean by writing it that way. And because I know the antisymmetric part is what's giving me the GM part, and the symmetric part is giving me the along-isopycnal and cross-isopycnal diffusivity, that may tell me a lot more. And it's important to note that when I do this too, I have not gotten rid of any rotational fluxes. They live in there. There are rotational fluxes still. It's that I've now parsed those rotational fluxes into where I want them to be in this tensor formulation without worrying about trying to separate them out or say what part's doing what. The idea is it's sort of the wrong problem, the wrong question to ask. So if somehow we can measure this K, we could separate it out. And now I've written A and S. Let me flash back to this to see where I wrote these two things in their currently parameterized form, where there's 2 components. There's only 2 unique components here, right? KGMSX and KGMSY that appear again here and there with a positive instead of negative sign. When I measure this part, let's just look at that part. First of all, so when I measure K, there's going to be 9 components. I can compute the symmetric part, the antisymmetric part. The antisymmetric part is antisymmetric, as this matrix is. It's got to have zeros along the diagonal. And if I go across the antisymmetric direction, I just flip the sign. Psi2 minus psi2, psi2, psi3 minus psi3, etc. So there's only 3 unique components there. There are 6 unique components to S, but the other thing I do when I solve this also now, once I've got that symmetric part, so I get K, I add K to its transpose divided by 2, subtract K to its transpose divided by 2. When I add, I get S, the symmetric part. All symmetric matrices, symmetric square matrices, are orthogonally diagonalizable, if you remember from linear algebra. So I can now orthogonally diagonalize that part. And what I'm going to get is some eigenvectors that tell me the directions, the 3 directions in which that stirring is happening. and 3 eigenvalues, which are going to tell me the diffusivities in those 3 directions. And I've written it in a kind of a provocatively similar form where I've called these things, which would be the matrices of the eigenvectors, the R and RT. I've written them as rotation matrices, R, and they almost always are. But for all intents and purposes, we can assume they are here. And then now I get 3 unique components, the 3 eigenvalues, and I now have 2 different along-isopycnal diffusivities and a diapycnal diffusivity. I can check whether those are really isopycnal and diapycnal after the fact by looking at the directions of the eigenvectors in those matrices that I've computed. Likewise, notice the antisymmetric tensor actually has a 3rd component, this psi3, which is a little confusing. I'm going to wait for somebody to ask me about it if they're following this enough and they're interested in what that is. I can talk about it later. But so when I measure it, if I can measure this K, I can actually get a lot of information that tells me a lot about exactly what the eddies are doing locally. Okay, so here's the idea. How do we measure it? So this is, I'm first going to, this is just a quick description of a model setup. MIT GCM, 2,000 kilometers squared, 3 kilometers deep, 5 kilometer res, 40 levels. There's a topographic feature in the middle. There's a wind stress blowing across the top. It's open on these ends, and it's got no slip walls in the northern and southern boundaries. It's got a temperature restoring at the surface. And so you get something like an idealized Southern Ocean kind of flow with a little topographic disturbance so that it's not zonally symmetric. That's an important thing, but we want it to be true, to try to do this in 3 dimensions. And you spin it up. Okay. And then what? So how do we measure? The goal is now to measure that K. So how do we do that? So again, same tracer advection diffusion equation here, Reynolds averaged. So everything looks the same here, but now I've said, suppose that now we don't just have one tracer field C, but we have capital N tracer fields, and I advect them with the same flow simultaneously. So for each tracer Cj, I have one of these equations, and I've got an eddy flux for each one of them. And for each one of those, I can write that eddy flux as this tensor times the gradient of the average of the jth tracer. If I now try to equate this to this, which I've written here, you can think of this as basically an overdetermined linear algebra problem. So this is 3 by 3. This is 3 by n, the 3 directions and the n different tracers. And this is 3 by n, the 3 directions and the n different tracers. So if those local mean gradients, at least enough of them are not lined up with each other, then I can use some kind of least squares method to invert this and get a best fit for K at each location. This is a method that was devised by Plum and Mollman for GFDL atmospheric model to look at stratospheric tracers in the 80s. And in some more recent papers, it's been done in a 2-dimensional framework, which allows a lot of simplicity. Basically, then in 2D, you can use a zonal average, and everything becomes a lot easier. But we really wanted to avoid that here and figure out whether we could do this in 3D with a 3-dimensionally inhomogeneous domain. And so, yeah, this was done more recently by Scott Bachman and Baylor Fox Kemper, Frank Bryan for an ocean model. So here what we did is in that idealized model, we put in 10 tracers, run them for 50 years. Each one is slowly, linearly restored to a target field. So each of those 10 tracers, if I just put them in and let them go, they're just going to eventually get all diffused away. So what we do is each one of them gets slowly restored with a right-hand side term like this, minus tau over 1 over tau times Cj minus Cj star, some target field. So that would be on the right-hand side up here for these equations. What well, not these because it's not Reynolds average. We were putting these in the high resolution simulation. Those different target fields, let's look at the first one, C1 star. The first tracer, C1, is being restored towards just a linear gradient in Y. L is the extent, the north-south extent. C2 is just a linear gradient in Z. C3, I can't do a linear gradient in X because it's a zonally symmetric channel, but I can now make C3 like the lowest cosine mode that fits in the model. So I'm going to restore that tracer to this guy. And then I have a whole bunch more. I want to over-determine the problem to make sure at every location I've got enough. You know, if I knew in advance that I really only need, hypothetically, 3 tracers to do this, then this problem would be nicely closed. The problem is, if I only use 3, it's very likely that as eddies move things around, there will be regions in the domain where the gradients are lying on top of each other, and I don't have a well-posed problem anymore. Our average is going to be, for this model, which doesn't have seasons, just a full-time average plus a lateral spatial coarse graining over 50-kilometer boxes, and that will define the mean. Okay, so here's the butter from this. So what I've shown here is kind of just visual demonstration of how well this works. So I'm just looking at 2 of those 10 tracers, C3 and C1. Those 2 were, C3 is the one that's being restored to a cosine in X, and C1 is the one that's being restored to a linear gradient in Y. So the colors on the left are the target field. So there you can see that cosine in X and the linear gradient in Y. The contours are the actual mean that evolves, right? Because it's a slow linear restoring to the target field. So the actual mean will be a result of that plus whatever eddies are doing to mix things around. So in fact, to not a too bad degree, those tracers, C1 and C3, the averages of them do take on, you know, roughly something that's mostly got gradients in X and roughly something that's mostly got gradients in Y. So then the primary gradient in C3 is going to be dC3 dx, right? And you can see it's got, you know, largely kind of constant in the vertical, and we got its gradients this way. dC1 dy is almost constant, meaning it's almost constant gradient in Y. Then of all the fluxes, you know, which flux is going to be most interesting to look at here? So there's, you know, 30 different fluxes, 10 tracers, 3 directions. I've chosen here just the zonal flux of this tracer C3. So that's the flux in the direction, which is the direction in which there's a gradient in this tracer. And what you can see is that roughly looking here, you know, positive there, negative there, positive there, looks kind of down gradient. If I now I do that problem, we've constructed that K, done this least squares problem at every location in the domain after defining the average and the mean, a lot of work done by Drove Belwada, postdoc who was working with me, who did all of this. I should have mentioned, and I won't be sure again to mention at the end, a great scientist who's now at University of Washington. You know, if you guys are going to hire more oceanographers, you should consider him too. I know you've got one coming, but you could always use more. Anyway, so just compare these 2 fields. This is the one component of the reconstructed Eddy tensor in the C times the gradient of C bar 3 in the X direction, which is a representation of this. So it's just, the point is just they look a lot alike. So the reconstructed field has done a very good job at representing the flux. Likewise, for the meridional flux V prime C1 prime and its reconstruction, also very similar. So I'll get a bit more quantitative about how similar they are, but first let me show something else, which is, so the way we constructed that tensor K is by using these passive tracers, and then I've just compared its ability to represent the fluxes of those same passive tracers. A harder test is to try to see whether that K, which should be kind of, the idea is it's a universal property of the flow, and it doesn't matter which tracer you look at, In this model, temperature is buoyancy because there's no salinity and there's a linear equation of state. So T and buoyancy are equivalent. So now if I look at the temperature fluxes in the zonal direction, 1,500 meters in the meridional direction, and then look at their reconstructions using that same K, which did not take into account any of the temperature or buoyancy information, nevertheless, it does a remarkably good job at capturing those fluxes, both in plan view at 1,500 meters, and this is a slice, XZ slice at y equal right in the middle of the domain. They look quite good. We can go even farther and be more quantitative and compute an error, the difference between the actual flux, the reconstructed flux divided by the actual flux in absolute value, and then make histograms of these. And in fact, overall, you find that the errors are pretty low. So it does a quantitatively good job in most of the domain in reconstructing these fluxes. Okay. I'm not going through all those slides. I will cut forward a little bit in a few places, because also I don't know how much of any of this everyone's following or not, since I'm not getting questions, and I can't see faces. But so basically now, so far we've shown that we've got this problem of how do we measure fluxes. It's difficult. Here's a method. Throw a bunch of tracers in, maintain some mean gradients. You can extract this construct K, this tensor. And now, so to make it clear, you know, that tensor is a function because our average is a time average and it's coarse graining average. Basically, this has as many components. It's got 9 components and as many spatial points as there are 50-kilometer boxes. So we've computed this for many places in the domain. So it's a 3-dimensional. Each of its 9 components is a function of x, y, and z. Now we can try to understand things about the theory and what we found, right? So we can now do this thing where we now, before I've just looked at how well it does to reconstruct the fluxes, so now we can actually decompose that into a symmetric and antisymmetric part. The symmetric part locally, every place we solve this little eigenvalue problem for the symmetric part and get the 3 eigenvalues, and look at the directions in these eigenvector matrices. And maybe the first thing to point is, so these 3 directions, if it's really picking out isopycnal and diapycnal, then the eigenvector associated with the small eigenvalue should point directly in the diapycnal direction, directly across the isopycnal. So this histogram is a histogram of the difference between the actual isopycnal angle. So here's an isopycnal. Imagine it's sloped and there's a normal to it that's got some angle beta iso. And then you can compute the actual, the kind of beta, the angle in that 3rd eigenvector associated with lambda 3, and then look at the difference. And in fact, it's largely peaked around 0, meaning that in most locations, this method is actually picking out the diapycnal direction and the 2 isopycnal directions and finding diffusivities in the cross isopycnal direction and the 2 directions along isopycnal. Now again, if it was Redi, I would just have those 2 be equal. But in fact, there's a whole other interesting story here, which is now if you just imagine in a 2D world and how turbulence disperses a tracer in 2D, well, if that 2D turbulence or field is isotropic, it should spread things equally in both directions. But if I impose some local mean flow, which there is all over the ocean, some kind of local jet, you will find that you have a much larger diffusivity in the along jet direction, along the isopycnal, than in the cross jet direction that's along this isopycnal surface. And that's now the difference between lambda 1 and lambda 2. Lambda 1, so locally, these 2 directions are represented with these little markers here, and they're roughly giving you sort of the along mean flow direction and the cross mean flow direction. So lambda 1 is the amount of mixing below that 50-kilometer scale in the along flow direction. It is larger. It's on order 20,000 meters squared per second, and the cross flow direction here, this is the one where most theories are really thinking about this cross flow diffusivity lambda 2, and it has values of an order thousands of meters squared per second, which is, by the way, the value found by practically every experiment that goes and throws tracers or buoys in the ocean and watches and tries to measure their mesoscale diffusivity along an isopycnal tend to find values like that, on order of thousands. And then the diapycnal turns out to be small. It looks like it's bigger than it actually is, and this gets into a story. I don't have enough time to explain that. There's some errors in there, but the main thing is this is incredibly small compared to that, and the directions are correct. I'll try to kind of speed up here and get through the point. Maybe I'm going to, symmetric of this, there's a lot of interesting stories there, but in a nutshell, if we back things out and assume that the psi2 and psi1, there's a way to extract the GM part from those, which is, that's where the GM part sat in the Griffey's form of the GM parameterization. You can back out what KGM should be, say, at 1,000 meters depth. So the lateral adiabatic part of the buoyancy flux. And here now you find values of KGM that are on order of hundreds. This is also consistent, which is with what's known from modeling experience, where if you're a modeler setting up your model in a low resolution run, you've got GM on because you have to get the isopycnal surfaces right. The main thing you're going to tune is the GM coefficient to make sure that the mean slopes of isopycnal surfaces are roughly like what's observed. When you do that, modelers typically find that you need to adjust KGM to be on order hundreds, as is found here. And note that that is very different from the values of thousands found for the along-isopycnal diffusivity. And by the way, really quick, this is from a paper by Untitled et al. In 2013, showing basically that I'm running out of time, that if the global oxygen distributions vary hugely as a function of how you set that Redi coefficient. And he noticed that, in fact, the idea of demanding that Redi always be equal to GM means that you're setting Redi to be much too small, because GM is roughly hundreds and Redi should be thousands. And this leads to a great decrease in ventilation of oxygen and leads to hugely wrong oxygen distributions in the ocean, which I'm not spending enough time explaining this, but there's a big effect for not doing this correctly. And I think in the interest of time, I'm going to skip the theory part here and say that there's actually an underlying theory that relates the GM and the Redi part, and it seems to hold up here. Maybe this is a good picture too to see the two. Here's horizontal slices, XZ slices, YZ slices of the Redi part and the GM part. They're very different in vertical structure, very different in magnitude. And if you don't do those things correctly, your model flow is quite wrong. And there is a way to relate these two theoretically that tends to work pretty well. But I'm going to stop there so I don't go over time, and you can ask me questions about the parts I skipped over. Maybe I'll just go through my summary and then I'll stop. So argue that, that if you set the Redi part, the along-isopycnal diffusivity, and the GM part, which is relaxing isopycnals, to mimic the effect of missing baroclinic instability, if you set those two equal, and you've started by setting this, you're going to have a too small Redi coefficient, and that's going to lead to a very sluggish eddy transport of tracers along isopycnals, sluggish transport of oxygen, which is the ventilation that replaces the oxygen that's taken up by bacterial decomposition of organic matter in the dark interior of the ocean, and you get very wrong oxygen values. And just again, that tuning shows you that should be around 500, whereas observations of tracer diffusivity tend to give you around 5,000. So they really aren't the same. They're both depth dependent too, and there's a way to fix this and maybe a way to actually relate these in an appropriate way in an ocean model. Okay, I'm done.
Thank you, Shafer.
Sure. Maybe I'll, so I can see you, I'll stop the share and then I can put it back on if somebody's got a question.
Yeah, do we have any questions? Elizabeth, go ahead.
Hi, Shafer. That was cool. So it's kind of embarrassing. I sat at NCR all that time, and yet I was terrified to ask Peter Gent about what is Gent-McWilliams and how does it work. So this was a nice overview that was like, okay, I can follow this. Next time I see Peter, I can say, okay. So if I understood this correctly, what you're doing is you're showing that by setting diffusivity due to Redi diffusivity along isopycnal equal to GM, you're totally messing up the diffusivity along isopycnals.
Yes.
And that's probably important for, outcropping, for temperature advection, all sorts of different climate phenomena.
Yeah.
My question then is, as our climate models are getting more and more from this 1 degree not eddy resolving into the eddy permitting and eddy resolving spaces. I mean, some of the high resolution models, a couple stuff I'm seeing now is at 0.1 degree. So you've suggested an approach that a different way of setting K-Redi and KGM. Are these type of parameterizations scale aware as our models start getting more and more high resolution and we get to the point of maybe we start turning off Gent-McWilliams?
Yeah, they can be made scale aware. That's a whole can of beans, and there's a lot of work going on in what's called the gray zone, where you partially resolve eddies. I'm involved in this climate process team that's being run by Lorzana, that involves people at NCAR and GFDL and a number of other people. And one of its goals is to understand how to parameterize things in the gray zone. It's not so explicitly focused on tracers, but there is a way to do that that's not addressed at all in anything I said. I would claim that while, yes, there exists now some high resolution coupled climate models, we are a long way from being able to not, to avoid the use of 1 degree and lower resolution models for very long term. I mean, I don't even know for the current, the next instance of the IPCC report. I think the ocean models in those, I don't think it's even a 1/4 degree. I think it might be, which is, you might argue is a bit in the gray zone already, but I think we're going to be, need kind of straight up no gray zone parameterizations for a while too, but also it can be done.
Cool. Thanks so much. This was great.
Thank you.
Any other questions? Dan, go ahead.
Hi, thanks. That was very interesting. I'm also wrapping my head around it. You've calculated then these coefficients for each location. Is there, like how is this then? How would you then transfer this into, say, a climate model where you can't back these out?
Right. Yeah, so I didn't explain that very well. Thank you for asking that. So because I rushed a bit at the end. The main point here is not to get the values that we would use in the climate model. It's to be able to simultaneously measure in a reasonably realistic, 3-dimensionally non-isotropic, non-homogeneous model, those 2 coefficients at each location. In fact, there's not just 2 coefficients, there's other things, right? All the components of this tensor. And the point being there is that now we can explore the theories that tell us how to set those coefficients locally from, resolved scale parameters in an ocean model. So a more sophisticated, better tuned, flow dependent diffusivity parameterization for ocean models. And currently there is no flow dependent parameterization at all for Redi. It's just set equal to KGM. So even though there's been a lot of work into, making GM vary horizontally and vertically with the flow, depending on the background mean flow, for example, and the deformation scale. It's still the case that they just set Redi equal to GM in most cases. Or there's, without that, if they know they want to turn it up like a non-Desigan study, it's just a constant value. It just cranks up the constant value everywhere. So it's to basically, yes, it's to inform our, being able to do this now is the first step to actually dig into the theoretical relationships between these.
And then just a quick follow-up. I think Susan Lozier gave a talk showing that observations of transport associated with thermohaline circulation, in observations is far more, like there's a lot more interior transport than you get out of current generation of climate models.
Oh, yeah.
Does that also relate to this, that the diffusivity in the climate models is just...
say the work again.
Susan Lozier.
Yeah.
And
it was
showing using that, like using observations or using, I think maybe Argo, that transport in the actual ocean. There's a lot more interior pathways than, climate models tend to confine everything right along the boundary currents and whatnot for the
yeah.
I think, and actually Elizabeth can correct me on this, but I'm just wondering if there's a relationship here between what you're doing and that, or if that's just...
I mean, there should be. I don't know offhand, but hypothetically, it sounds related. Like this sounds like additional research demonstrating the complexity of the tracer transport in the ocean, right? And this is an attempt to sort of ferret out the best way to parameterize it. So they ought to link up, but that's pretty far downstream from where we're at right now.
Well, it looks like really cool work. Thanks.
Thank you.
It looks like Brad Pierce. Go ahead.
Hi. Can you hear me?
Yes.
So this might be a naive question, but what are negative diffusivities? The Ks, you showed a lot of Ks that were negative.
Oh, did I? They shouldn't be. So okay, it depends on which part, which one I was showing.
Particularly for the GM ones.
Right. So that's and it might have been, I can't remember which picture that I showed. Maybe I could let me at least look myself and see if I can remember which.
Even some of your last figures, you showed some right near the equator throughout the depth, and then you also showed some near the surface at the equator.
You're right. So let me reshare this just to make sure everybody sees what you're talking about, because it's true and it's a good question. Very reasonable. Problematic. Share. So this is what you're talking about, right? This is one of them?
Yeah.
So
yep.
It's pointing out is that there's a lot of blue in here, right? That looks a little bit negative. And this is that you should not interpret that as meaningful in a nutshell. There are small negative values. There is a way to understand how you can get that has to do with the fact that there's a whole bunch of stories in here that I didn't get to. Well, let me keep the story simple. The simple answer is we are by no means suggesting that you put a negative GM diffusivity in your model anywhere. Let me leave it to say that this is sort of an understandable error that is correctable, and that the bulk features we're looking at about is where this this value is strong and how it relates to the vertical structure of the Redi part. This is sort of an unfortunate figure that I stuck in a while ago and should have replaced with more recent example. That's a little bit of a kludge of an answer, but
okay. So,
yeah.
but
there's
probably not.
So one thing you do when you measure the Eddy fluxes too, if you know one thing, if you just think of it as locally a static diffusivity, you're ignoring the fact that there are also Eddy transports. So meaning that the background velocity is actually transporting prime quantities, right? So when we pose things as a local diffusivity, we're assuming that everything that the transport by the resolved mean flow of any variance into a region is negligible or zero. When you have that, it can contort, in particular, the interpretation of the GM part from these, which we've gotten by measuring these three stream functions in the antisymmetric part, which are intrinsically, well, they're stream functions. It's going directly from those to a diffusivity. So if you don't have kind of the perfect Platonic setup, when you back out a diffusivity from those things, you've got transport effects, you'll find some negative values.
Okay.
It doesn't actually explain the negative values you pointed out there, but it explains them in some other places. I better stop. I'm talking over my words, but
So kind of a follow-up question. For your GM formulation, you needed to rotate it so that it was aligned with the isopycnals? What?
No.
How would this? No.
The Redi
Okay.
part.
The Redi part.
Right.
Okay.
So the Redi part, it's like you just measure this tensor. It is what it is. I can get an antisymmetric part and a symmetric part. The symmetric part, I can now, it's orthogonally diagonalizable. So I do that. When I orthogonally solve the eigenvalue problem locally, I get 3 eigenvectors and 3 eigenvalues. And the eigenvectors point in the different directions that the eigenvalues are acting as diffusivities.
Okay.
Is that what you're asking?
Well, I guess I'm wondering how this parameterization would change if you were actually using an isopycnal vertical coordinate.
Oh, yeah. Well, yeah. That's,
and how much is that? I know Reiner Bleck did a lot of that years ago. How much is that has been incorporated into the climate modeling?
A lot. So MOM6, which I learned this morning from Elizabeth, NCAR is also moving to MOM6. That's GFDL's model. It is an isopycnal coordinate in the interior.
Okay.
And so there, if we only lived in an isopycnal world and used an isopycnal model to measure these things, it's actually a lot easier. So a lot of this is very much geared at z-coordinate models.
Okay.
Which might be a fair criticism, except for the fact that, let me think. So, you'd still, so I think if I was going to start by trying to do the same experiment with an isopycnal model, my tracers now, I don't have to worry about the diapycnal part. But along each isopycnal, I still need at least 2 tracers with gradients in different directions to measure the 2 along isopycnal directions. And then the antisymmetric part, it's a good question. I am.
It'd be interesting to see if you see the same kind of. I mean, I would interpret the negative Ks as numerical artifacts that are probably pointing to numeric issues. And I wonder if you'd see less of them if you did the analysis in an isopycnal model, since things are then larger scale in some sense.
That's reasonable to guess. I think that also the problem is even now in the isopycnal framework, what I'm getting a little stumped thinking about is measuring what is the antisymmetric part. What does this mean? So now you effectively have a bunch of tracers that you can treat as sort of 2D along isopycnals. So you have this kind of horizontal 2D picture. And now when you break that up into a symmetric part and an antisymmetric part, actually the only antisymmetric part you're getting is this what I called psi3. You don't actually get the psi1, psi2 that are part of GM. You have to get those from the fact that your symmetric part now has the thickness diffusivity that is adiabatic. And so I'm actually not immediately sure how to separate that part from the tracer diffusivity, but it's a good question. So it's a worthy thought puzzle that I don't have an exact answer to. So, thank you.
Cool. Okay. Well, thanks everyone for your good questions, and let's thank Shafer again for an excellent talk.
Thank you again for inviting me, Sam. It was nice. I still hope to actually visit in person someday.
That would be great. Yeah.
All right. Take it easy, y'all.
Thanks. That was